Hello, welcome to the Chidon Hamada Yerushalmi, the 2012-2013 edition of the Jerusalem Science Contest, brought to you under the auspices of Dr. Joseph Walter and the Walter Science Center. I'm Dr. Art Friedman, and I will be your instructor for this contest. We are going to have 12 lectures, approximately one a week. And the subject of the contest is astronomy. We're going to be using this particular textbook, Astronomy Today by Chasen and Macmillan, and this is the 7th edition. The last time we did this astronomy contest, which was about 5 or 6 years ago, we used the 5th edition of this book, and there's been a lot of new developments, of course, in the world of astronomy that are not in the older edition, so we've decided to use the newer edition, even though it is about 125 pages longer than the previous one. This also necessitates my having to pick and choose exactly what it is that I'm going to teach you, although I strongly recommend that you read the entire book for purposes of your taking examinations. I'm only going to hold you responsible for those particular topics that I am discussing. So if it's something, if we're doing a couple of chapters and there's something that's in the chapter, but I didn't talk about it in the lecture, it's not going to be on the exam, and that will make your lives a little bit easier. Okay, having said that, let's get started. We're going to be looking approximately 2 chapters a week, and what we're going to be doing first is chapters 1 and 2. So chapter 1 in this book is called Charting the Heavens, and chapter 2 is the Copernican Revolution. So we begin with something that you find in almost every single science book. Whenever you're studying science, they always talk about the scientific method. One of the things that I don't like, though, is that in your book, the scientific method is kind of, the way it's presented is a very, very simplistic way of doing this. It just shows observation, really only has 3 parts: theory and prediction. And it shows this as a cycle. It gives you the wrong idea because it says that observation leads to theory and theory leads to prediction, and predictions may give you additional observations. I don't really like that particular model. Many of you probably have already seen or studied the scientific method, but for those of you that haven't, I would still start with observation because that's what really prompts a scientific investigation. You observe something, you see something in your natural environment, but we don't go directly to a theory, as it says in your book. We have a hypothesis, and this is some idea that we have about an explanation about what it is that we're actually observing. Now, the hypothesis would actually have some predictive value. So this is where I would put prediction here. The hypothesis should enable us to make predictions. And our predictions, we should be able to verify by tests. So let's put test in here now. And test could be experimentation, although there are other forms of test. And then what's going to happen now is these tests may cause us to have additional observations, or what may happen is that our tests, if they're not consistent, will cause us, if our tests are not consistent with a hypothesis. So if it's inconsistent, we have to modify our hypothesis. But if we do our tests over and over and over again, and not only have we done them, but some other groups of scientists have conducted the same test, and we've done this hundreds, maybe thousands of times, and our predictions are always borne out, our hypothesis is always borne out by the test of the predictions that we have, then eventually our hypothesis may lead to a theory. Now, we can never prove a theory, we can only disprove it, because if we find one example that contradicts the theory, then we've got to go back and start over again, because then we know that our theory is not valid. So we can have a million things that verify the theory, and then one thing that shows the theory that's wrong, the theory is incorrect, or the theory does not support that observation. So then we have to go back and modify, come up with a new hypothesis, and start the entire process over again. So this is a scientific method, and in ancient times, people made observations, but they didn't really have the scientific method to use. So it was a little bit different when they made their observations. So one of the things that people did was they looked up at the heavens and they saw stars in the sky. And one of the earlier explanations for what was going on was that the Earth was stationary. The Earth is the center of the universe. It's what we call a geocentric universe. And imagine you're sitting still and everything around you, everything else in the universe is rotating around you. And so, from that particular frame of reference, that's what ancient peoples thought. So here's the Earth at the center, and around the Earth is a sphere. Of course, I'm just drawing it as a circle, but it's a sphere, and this is what was known as the celestial sphere. And this is the sphere of the heavens. And all the stars are actually imprinted along the surface of the sphere. So that would also indicate that every star is equidistant from the Earth, although nobody really knew at that time how far away stars were. So people would look up at the heavens and they would see a constellation. And of course, in ancient times, people would see these things and they would look at them and think, well, these must be our gods. This is what we're seeing in the heavens here. And, the ancient Romans and the ancient Greeks had a whole pantheon of gods. And so they imagined that the stars, what they saw, actually were representations of various gods or various, what we would say, Greek mythological beings. So one of the things that you look up in the heavens, if you do this in the winter, it's one of the most prominent things that you can see in the sky. You have to pardon my drawing, which is not very good. But what I'm trying to represent here is the constellation of Orion. So we actually have a series of stars. There are actually more stars than I've represented here, but these are some of the more prominent stars that are in Orion. And people looked up at this and they saw what appeared to be a head and maybe two arms, a belt, perhaps a sword hanging down from the belt, and two legs. And the Arabs actually gave the names to many of these stars. So they called, they were some of the earliest astronomers, and they called two particularly bright stars here. This one was called Betelgeuse. And then there's a star down here called Rigel. And the head star, which is a further away and not as bright, is Maesa. And then the star over here, forming the other arm, is Bellatrix. The other leg star is called Saiph. And the three stars that form the belt here are, from right to left, are Mintaka, which certainly doesn't sound Arabic. It sounds more like it might be Japanese. I don't really know where that name came from. The central star is Al-Nalam, and the star to the left of that is Al-Natab. So these are the stars, and the modern designations for these particular things. It's in the constellation of Orion, as I said. Orion is the hunter, and this particular constellation, the way in modern times, the way we designate these things is the brightest star was given the designation Alpha. So this is Alpha Orionis, and Rigel, which is this, by the way, is a what we would call a red supergiant. And we'll talk about the colors and what the terminology supergiant means at a later point in time. This is a blue supergiant, Rigel, Rigel is expected sometime in the relatively near future will probably explode because Rigel is nearing the end of its life. So this is Rigel. It's a blue supergiant. If you actually look at these things in the sky, you can actually see the bluish color and the reddish color, particularly if you're looking at them with a telescope. You can see the colors of these two stars. So that's this is Alpha and Beta, and Epsilon is I have to look this up myself because I can't remember specifically. Alpha, Beta, Gamma. Well, the Gamma star is Bellatrix. So this is Gamma Orionis. This is Beta Orionis, Gamma Orionis. Delta is then I think we use the stars that are actually in the belt. So Mintaka is Delta. Alnilam is Epsilon. This is Zeta. That's Zeta. This star right here. And let's see, there's a couple others that I haven't labeled. Maisa is, I believe, Kappa. No, it's Lambda. This is Lambda. And Saif, I think, must be Kappa then. This is Kappa. So these are how we designate these stars today. But if we were to actually look at these stars, not head on as we're doing now, but let's say we took a different view of this and we looked at them. What I just put up on the board, by the way, is not in your book. But the following is, so if you were to actually look at these things, here's your eye, and you're looking out this way, and if we say that epsilon, which, let's see if I actually have this, what I wanted to show you. Yeah, epsilon is Alnilam. So if we're looking out towards Alnilam, that is the central star in the belt, Epsilon Orionis, we would actually find that the distance from us to the star is 1,340 light years. And a light year is approximately 6 times 10 to the 12th miles, if we want to do it in miles, 6 trillion miles. So we're talking about a pretty big number there. And so this is 1,340, so that's, actually makes this something on the order of about 8 times 10 to the 15th miles away from us. So it's a very great distance. Something that could not even be imagined by ancient peoples. We also have the alpha and the beta that I wanted to put in here. The picture in your book actually is a little bit more complete than this. So this is 643 light years, and that's Betelgeuse. And Rigel, by the way, the word Rigel in Arabic means foot. It's probably not pronounced that way, but it sounds and looks very much like Regel, the Hebrew for foot. So you can see that they have the same root word, same derivation. And actually, the beta Rigel would be directed this way. This is beta. This is alpha, and that's this 1340 refers to this, and this is about 772 light years. So the point being that even though when we looked out into the sky, certainly ancient peoples looked at this, they felt that this was all imprinted, all these stars were the same distance. You can see there are considerably greater distances or lesser distances. They're certainly not in a plane in any way, shape, or form. And if you were to actually look at this constellation from some other perspective in the sky, you wouldn't even see this at all. You wouldn't see Orion. You would just see these particular stars, and they would have an entirely different perspective from a different angle. Okay, so we've got this idea of a celestial sphere. And if we look at the celestial sphere, the Earth, as I said, is stationary. It's at the center of the sphere, and everything else is rotating around the sphere. So if we were to actually look at the sphere, here's the equator of the celestial sphere, and this is north. So the Earth is in here. If we look at the Earth's north pole, and then we extended that out towards the heavens, we would be at the north pole of the sphere, and there's a star there that's called Polaris, which is the pole star, the North Star. And we'll also find that the constellations seem, from the perspective of the stationary observer on the Earth, they seem to be moving, not if you were at the equator, they don't seem to be moving right along the equator, but they seem to be moving above and below the equator, which is the reason why, through the course of the year, the constellations sort of march. You can see certain ones at certain times of the year, and then they will fall below the equator or fall below your line of sight. You won't be able to see them anymore unless you're in the southern hemisphere. So they will illuminate that particular part of the night sky. But the point was that all these things, because the Earth's axis, its rotational axis, is actually tilted 23.5 degrees from its orbit, from the way that it's actually orbiting around the sun. Because of that, it looks like everything is marching at this 23.5 degree angle. And this imaginary line that the sun and also the various constellations seem to follow during the year is called the ecliptic. And so you've got this this angle here that represents the difference between the equator and the ecliptic. Okay. I want to talk about another definition that's in the book, which is solar versus sidereal time. So when we talk about a day, a solar day is a 24-hour day. It's the time that it takes for us to rotate. Let's say it's 12 noon. The amount of time that it will take until it's again 12 noon is exactly 24 hours. Now that's what we call a solar day. We're rotating around to the point where the sun is at the same position in the sky. However, if we do this in the evening and we're looking at the stars in the background, we have what's known as a sidereal day, and that's the time that it would take us to rotate to the point that we see exactly the same stars in exactly the same position that we saw the evening before. At that particular time, it's not 24 hours. It's about 4 minutes less than that. So it's about 23 hours and 56 minutes. 23 hours, 56 minutes for a sidereal day. The sidereal is based on the stars. And this has to do with the fact that the Earth isn't just rotating on its axis, but it's also moving around the sun. So it's moved approximately 1 degree. It's 1 over 365.25, slightly less than 1 degree around its orbit around the sun. And because of that, it has to rotate a slight distance further to get back into its original position. And so that takes approximately an extra 4 minutes for that to happen. So sidereal time and solar time are not exactly the same. There's that slight difference. Now, this business about the ecliptic is also important when we're considering things like seasons and why it is that the summer is hotter, for instance, than the winter. One of the reasons, of course, is the summer is hotter than the winter is because of the fact that the sun is actually higher in the sky, and it actually winds up being the days are longer in the summer than they are in the winter. So that means that we have more sunlight, more time for the Earth's atmosphere to be heated up, and as a consequence, of course, you would expect it to be warmer. But there's other factors, and a more important factor is actually, and the reason that there's such a big disparity between the temperatures in the summer and the winter, not so much the length of the day, which might contribute to a few degrees, but we have really enormous differences between summer and winter. And that has to do more with the fact that because of the fact that there is this disparity between the the so-called equator, celestial equator, and the ecliptic. Because of that, what you're actually finding is that at different times of the year, the Earth is presenting a slightly different aspect to the sun. So at some times of the year, sunlight, let's say we live up here somewhere, sunlight is coming in like this. Sun's over here, and sunlight rays are coming in almost perpendicular to the surface of the Earth. In the winter, it's presenting a different aspect. So now in the winter, sunlight is coming in more like this. And because of this more oblique angle, you're actually getting less sun per area of the Earth's surface. So less sunlight is actually falling on the planet during the winter. Even though the sun might be overhead or wherever it happens to be, it's still, the rays are coming in at a more oblique angle. So that's the reason that the summers are much hotter than the winters. Not as some people, when I ask the general population, people that haven't studied astronomy, if I were to ask a group of people, I would find that generally the answer that I get is that the sun is closer, the Earth is closer to the sun in the summer than it is in the winter, and that's the reason that it's hotter. And it's exactly the opposite. The Earth is actually closest to the sun during the winter, and furthest away during the summer. So this is the reason that we have seasons. There's one other aspect to the Earth's rotation and to all this other business, which is the fact that not only is the Earth rotating like a top, slow-moving top, but if you've ever seen a top spinning, you know that a top starts out and it's spinning about its axis like this, and then it begins to wobble. It goes like this, and then it goes like that. It's wobbling around. And so that wobble, the wobbling top, traces out something that looks like that as it's wobbling. So here, it's just rotating like this. Here, while it's wobbling, it's rotated. The wobble is making it trace out something that looks like that, and we call this wobble precession. And the precessional orbit that this is taking, the Earth is actually precessing on its axis. So the Earth not being up and down like that, being like this, this is actually moving like that and around like that, but very, very slowly. About 20. It's going to take about 26,000 years to complete one precessional orbit. So the Earth is actually moving because of this. What's actually happening is that what we see overhead as the North Star Polaris is actually going to change. And about 12,000 years from now, the pole star will no longer be Polaris. That will have moved because of the precession of the Earth. And we're now going to see overhead, we would see the star Vega in the constellation Lyra. So Vega becomes the pole star. And this, of course, is also going to have major climatic effects as well. But we're talking about something that is, in the very, very distant future for that to happen. But it's actually going to change, will change the weather patterns on different parts of the Earth. Okay.